Welcome back. In this video, we'll look at Theorem 1.2.2, the solution set of any homogeneous linear system of m equation in n variable is a, and this is what we've been working for during the last video. We want to prove that it's a subspace n variable, so of Rn. From what we've seen during the last video, the fact that the null space is a solution set, what we could say is that this is equivalent to saying that whatever matrix you have in m by n, the null space of A is a subspace of Rn. And it turns out that that's the statement we'll prove, and we'll prove it using this description right here of a subspace. We're going to look at things that get multiplied by A and give 0. All right, so we will prove the three properties for the null space of A. All right, property 1. I need to prove that the 0 of En, oh, sorry, let's put En here. Because Rn is really just a set, we want the set with the operation, and so that's the Euclidean vector space, and so I want to call it En. So 0 is the 0 of En. We need to prove that it's also in the null space of A. And remember, null space of A is the set of all x, so that Ax equals 0. And so if I multiply A by 0, I'm going to get A times 0, 0. That's just going to give me 0, 0. A different size one, right? This is in Rn, this one's in Rn, this one's in Rm, but they're still the 0 vector. And so, yes. Another way of proving this property is to say that the trivial solution, the 0 solution, is always a solution for the homogeneous linear system. All right, second, let me take two elements, v and w, in null of A. And so what we know, what we're given, is that A times v is 0 and A times w is 0. And I want to prove that the sum is still in the null space of A, so let's look at what happens if I multiply A by the sum, and then I get AV plus AW. I get 0 plus 0. I get the 0 vector. And so yes, V plus W is again in the null space of A, and so the null space of A is closed under addition. All right, part 3. I'm going to take V in the null space of A, and I'm going to take K in R. So we know that AV is 0, and now we want to look at A times KV. K is just a real number, so it commutes with the matrix. I can move it through the matrix, and I'll get K times 0. I will get 0 again. And so yes, KV is in the null space of A. And so all in all, what we've proven is the three properties are true, and so null of A is indeed a subspace. All right, so that's the proof. And let me say part 1, this part, proving that 0 is in it, is as easy with a homogeneous linear system and solution, but 2 and 3 would be a tiny bit more, especially 2 would be a tiny bit longer if we didn't actually talk about the null space. So the null space is nice, and it's going to come back later when we talk about linear transformations anyways. All right, so let's just finish this section. Let's look at example 1.2.9. I want to show that this set U is a subspace of E4. So I want to take all vectors W, X, Y, Z, so that X equals Y plus Z minus W and 2X minus Y equals 3Z. We want to prove it's a subspace. I could prove the three properties, but now we have this theorem that we just proven that says if I could write it as the solution set of a homogeneous system, or if I could write it as a null space, it would actually do all the work for me. All right, so we want x equals y plus z minus w, and we want 2x minus y equals 3z. And so if I want to write this as a linear system, I would put it all on one side. So w plus x minus y minus z equals 0, and 2x minus y minus 3z equals 0. And so you could see it as the solution set of this, which is homogeneous, and so it is a subspace. Sorry, I'm a bit low on space. And so yes, U is a subspace. In fact, I mean, you could use that U is the null space of something. So here U is the null space of the matrix 1, 1, minus 1, minus 1, 0, 2, minus 1, minus 3 if you wanted to. All right, so either way works, and we have a subspace like we had to prove.